Okay, welcome everyone to my continuation of what are my favorite theorems, a very biased collection as usual. Today there will be a theorem, but really what I'd like you to keep in mind is that I'm going to present it more like an approach, a strategy towards something. We'll see what it is. It will be transcendent numbers, and there's actually two approaches, and one of them is due to a German mathematician called Mahler, and the corresponding type of functions are called Mahler functions. They're kind of motivated by fractals, so that's why I call it self-similarity. We'll see what that means. But let's just jump right into it. Okay, so what is this all about? This is all about transcendental numbers, kind of things that are not roots of polynomials. So if you think about the real numbers, you could think about complex numbers as well, but if you want, but let's think about real numbers. And the transcendental numbers make up almost everything. They could kind of show that very easily by a Cantor-type diagonal argument if you want. But they're kind of really difficult to find in some sense. So everything you ever write down should be a transcendental number and not algebraic, so not a root of a polynomial. But it's kind of really difficult to prove. And usually that's the whole point. So proving that a number is transcendental is difficult, and in particular that real numbers, so not real numbers in the sense of mathematics, but kind of the honest numbers, not made up numbers, not toy example numbers, to show that they are transcendental is like really difficult to use. So pi is a good example. Pi, everyone's favorite pie, very tasty, is a transcendental number, but showing that is like surprisingly difficult. Yeah, so showing that the number is not rational is kind of quite easy. Showing the number is not algebraic is kind of a very, very large difference. It's got a really huge step in difficulty here from not showing that something is not rational to showing that something is not algebraic. So most proofs of that numbers are transcendental, particularly the older ones, they're kind of really not good in some sense. They're just case by case picking, and then just some very complicated type of approximation type arguments. It can't be bigger than, it needs to be smaller than, blah, 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 something like that. It's really, really difficult. The made-up numbers are much easier. So here, Liouville's number, which was the first one to be shown to be algebraic, so transcendental, is very easy. You just put in ones, and the ones are so far spread out, namely with a fractorial, that it kind of can't be any algebraic number. But for real numbers like pi or e, and this is usually very tricky. And it took about till the 20s. So this was a very important question, kind of showing that something like some easy numbers are transcendental. So Hilbert had a problem on it, and a favorite list of Hilbert's problems. I think it was number 7. If it's not number 7, it doesn't really matter. There was a really famous problem Hilbert posted in the kind of the turn of the last century. So not from 20 to 21, but from 19 to 20, kind of proves that something is transcendental. And people were trying very hard, and roughly in the 20s and 30s, people developed machinery to prove that at least some things are transcendental. So instead of doing a case-by-case hand check, which is like difficult and nobody wants to do that, there's at least a machine that proves that certain type of numbers are transcendental. And there's a very famous one, the Geerfran-Schneider theorem, the Geerfran-Schneider theory, proving that something like, or kind of deciding whether alpha to the beta is transcendental. And there's a developed in the 20s and 30s, and there's an alternative approach due to Mahler, which I personally like a bit more, but it didn't become that famous, mostly because it shows that quite a few numbers are transcendental, but maybe not the most famous one, or not the most popular one. Anyway, I love it because it's kind of related to transcendental numbers. Yeah, sure. It's related to fractals, and that's what we are going to explore now in this video. Okay, I hope the setting is clear. We are trying to develop a machinery that shows the transcendence of certain numbers. And the main idea is essentially, let's look at fractal. So what is a fractal? If you don't know what a fractal is, that's some self-similarity, but you actually don't need to know that. The only thing you need to know is the Cantor set. So the Cantor set is, I hope everyone likes and knows the Cantor set. So you take the unit interval, you take out the middle third, and whatever you get, you take out the middle third of both, and you take the middle third, you always take out the middle third here, and so on. And whatever the limit is called the Cantor set. You can define that kind of more algebraically if you want, as follows. the Cantor sequence, which is essentially really just the Cantor set. So here's the Cantor sequence. If you write it the first values, is just for every n you put a 1 if the bot 3 expansion, so the this exponent 3 contains no ones, right? So here, if you want to think of it like 0, here's the 0 part, here's the 1 part, here's the 2 part, and you cut out those that contain no ones, and then you keep the other ones and you write a 0 otherwise, and you get this Cantor sequence, which looks exactly, you could kind of see it here already, like here the middle one is cut out, and the bigger middle piece is cut out, and the middle piece is cut out, and here's an even bigger middle piece that is then cut out, and so on. So the Cantor sequence is then just kind of the sequence of numbers mimicking the Cantor set. That's just it. It's just easier to formulate. For me, it's just better here in this video to formulate it as a sequence, right? You just write down the expansion with base 3, and you check whether it contains a 1 or not. And if it does not contain a 1, you write a 1. And if it does contain a 1, you kick it out exactly like here. You kick out everything that somewhat contains a 1, kind of in every kind of possible digit. You just put that in a sequence. Okay, and if you write down, and that's kind of now where this whole story starts, you write down the kind of the generating function of that piece, which is really just this formal expression, which has a pole at 1. So you plot this function, it looks like this, fine, between 0 and 1. And it's just this idea of putting a fractal in the generating function. So we have just now one function. This depends on omega or w, whatever. And it's just the sum over all of these beasts, where you just put in front of w to the nth entry of our Cantor sequence, which is either 0 or 1. So there are infinitely many that would sum up to 1 at 1. So the pole is at 1, and it kind of goes to infinity here at 1. And kind of the idea is always like whatever happens around the pole of a function is really the interesting part. And then Mahler observed, or someone observed, I'm actually not quite sure whether this one is due to Mahler, but someone observed that this sequence, this function is now a function. It's a function in a variable. And you can ask, does it satisfy some functional equation? And it does satisfy some functional equation. And the interesting one is, well, the function itself is here, and it calls itself with a higher power, right? So it's kind of some self-similarity of it. The function itself calls itself with some higher power and ignores the thing in front, right? So you have something like CW is actually something in front, God knows, times CW cubed. And the cube here is kind of this threefold self-similarity of the Cantor set. And that was already a really good step. So you have a function that comes from a fractal and it actually satisfies a recursion, a functional equation that kind of calls itself. So it kind of reflects the self-similarity. And then Mahler used that to show the following. It's kind of really exciting. It's kind of really exciting statement. So let's say you have something like that, a function on the unit disk, and we can go to the complex numbers here, and it kind of converges. So it has a pole at around the unit disk, and it's converging inside the disk. You could scale everything if you want, but let's just do it this way. Then this function, and it satisfies this function equation. So it's a very general thing. So the original function is here, and whatever this thing is in front, it calls itself with a higher power, it calls itself with the next power, it calls itself, and so on and so on. Very similar to what we have seen on the previous slide. So let's just go back, right? So very similar to what we have seen here. Just even more general. And there are some coefficients in front, and the coefficients can even be rational factors. And there is only one condition that needs to be true, only one condition that needs to be true, and it's essentially always true. I will go to the condition in a second. And then every such function will satisfy, is a transcendental number generator. It will satisfy, whenever you stick in an algebraic number, you get out a transcendental number. F of algebraic is transcendental. Essentially what happens is the fractal, you will see the example on the next slide, the fractal will kind of spread things so far apart, so weirdly apart, that they can't be algebraic anymore. But this is really cool. It's just a huge strategy to show transcendence, because any such function, and this is a really large class of functions, will satisfy this condition as soon as whatever the little condition here is satisfied. And the little condition is essentially, well, you look at the coefficients, they give you a polynomial. If you evaluate the coefficient at the radius of convergence at 1, it's just some polynomial you get, and that polynomial is supposed to have no repeated roots, which essentially always happens. So essentially always this polynomial has no repeated roots. Let me just say, essentially always, whatever satisfies such a fractal recursion will be a transcendental number generator, which I feel like is a pretty cool result. So let's wrap up with an example. So the original one, Liouville, was this idea of showing that something of this form here is transcendental, where you have, well, a k factorial in the exponent. And Mahler theory goes a bit further. It can show, so k factorial spreads out everything like hell. It's just super exponential. It's just crazily, crazily fast. And Mahler's theory, that a really tiny part of Mahler theory, will show that everything of this form is also transcendental, where alpha is any algebraic number. So alpha to the p to the k is a self-similarity with kind of the period. And this would satisfy the very simple functional equation of this form. And this is part of Mahler theory. You don't need to check anything. Whenever you fit in an algebraic number here in this sequence, you will get whatever 0.5, a half or something. You will get a transcendental number, which is like ridiculous because it's just very difficult to prove by hand, and it's just a special case of the theory of Mahler's. Yeah, I hope you enjoyed this video, this mixture between fractal geometry, if you want, and transcendental numbers, and I also hope to see you next time.